Did you know we can learn so much more from tree rings other than just how old the tree is? It's true. There's a field called dendrochronology, dendro meaning tree, chronology meaning study of time, where we can learn so much more about our past. Here we have a cross section of a tree that was cut down, sometimes referred to as a tree cookie. You can see here the various tree rings, representing different years of growth. Some of these rings are thicker and some are thinner. What causes those differences? Well, scientists believe that thicker rings are products of better growing conditions in that particular year. Here's another tree cookie. You can see here in the rings that some are thick and some are thin. Now, in a thick year, it's possible that the growing season was nice and long and there was lots of rain, which led to lots of tree productivity, more photosynthesis, and thicker rings. Thinner rings may be the products of droughts or shortened growing seasons due to delayed winters. So you may be wondering, is there a way to get this information about a tree's life without cutting it down? Yes. Scientists have ways of extracting information from trees using something called an increment bore, which I'll demonstrate out in the field. So I'm going to use some diameter tape to measure the diameter of the tree before we core it. Diameter tape is a little different than traditional tape because it factors in pi, because you actually measure the diameter, so the width of the tree, by measuring the circumference. This is why we get the nickname tree hugger. 43.4 centimeters. Next, we're going to use our increment bore to pull out a core to be able to look at the tree rings. So if you see, it's actually just a hollow tube that has kind of like a drill bit on the end. And typically we take cores at chest height. So we find a spot where there isn't a lot of thick bark, put a little pressure and turn, and it'll catch in the wood by itself. See, you don't even need me holding it anymore, and then kind of turn and go. Now, in order to age the tree, we try to get to the center of it. As you go deeper, it gets a little harder to turn. At this point, you might be wondering, doesn't this hurt the tree? Well, it's important to note that what makes up the tree trunk is mostly dead wood. The very thin living part is just behind the bark and barely gets damaged. The softer the tree, like pines and things, conifers, are a little easier to core than hardwoods, like oaks. So here's our extractor. We can measure it against this to see if we're in the middle. Looks like we're almost there. Get it in all the way. Now we're turning the other way. And what it's doing is breaking off the wood that's inside the bore from the tree. And then we'll try to pull it out. There it is. You can see the bands on there separate the different years. The thicker years, right, will have thicker bands. And those can be indicators of the conditions of the environment of the tree. So great years for growth, lots of rain, those bands will be wider. Those extracted tree cores are brought back to the lab where they are dried, mounted to wood, and sanded down with multiple grades of sandpaper to ensure that the tree rings are nice and easy to read and measure. Before they are measured, we typically age the tree and label particular years of interest, like you see here. Where the rings start to curve, that is the center of the tree. To measure the tree ring widths, we place the mounted cores on a moving stage like we see here with this Velmex Dendrochronology system. By looking at the rings through a scope, we can accurately determine when a particular ring begins and ends. The movement of the stage is connected to a device that converts the movement to lengths up to 1/1000th of a millimeter. As you can imagine, measuring tree cores this way generates a lot of data. Taken all together, we can plot the growth patterns of trees in an area over time, and it looks like this. We call this a chronology. Notice the data trends downwards. It's because rings tend to get thinner as the tree ages. Not necessarily because the tree is slowing down, but because the tree is getting bigger and it takes more wood to cover the tree. When we standardize the tree data to account for age, the chronology will look like this, where we can more clearly see climate trends from year to year. Often the rise and fall of the chronology can be explained by rainfall in a year or average annual temperature. One pattern that has emerged in many chronologies is an upward growth trend. This can be explained by the rising amount of CO2 in the air due to the burning of fossil fuel. More carbon in the air translates to more tree growth each year. Also, rising temperatures associated with climate change allow longer growing seasons for trees, meaning thicker tree ring. This tree hugger hoped you enjoyed this lesson about dendrochronology. Thanks for watching.